All right, in this video, I want to talk about the root and the ratio tests. So what I want to do first is I want to remind you what they say, and then I'm not going to give a rigorous proof, but I want to talk about the idea of the proof just to show you how that works. And I want to justify it a little bit. It's not a rigorous proof. A rigorous proof is in the book if you're interested. So let me remind you about the root and the ratio tests. The root test says, and I'm just going to, since they're so similar, I'm just going to word them together. But the root test says, let L1 be the limit. So here we're looking at the convergence of the series C sub n z minus z naught to the n as n goes from whatever, 0 to infinity. And so here we're going to look at L1 as the limit is n goes to infinity of the nth root of the modulus of C sub n. And what we're going to do is, so L1 is going to be this limit, and L2 is going to be the limit as n goes to infinity of the modulus of C sub n plus 1 over C sub n. So that's the modulus of C sub n plus 1 over the modulus of C sub n. And so these are the two values. Then our power series has a radius of convergence r equal to 1 over L1 and also 1 over L2 if these limits exist. Okay. If you've ever taken a course in real analysis, and I understand that that's not everybody, but if you've ever taken a course in real analysis, the actual theorem, so this is what I'm saying is true, but the actual theorem is actually you replace the limit with the lim sup, and then that always exists, and then that'll give you L1, likewise for L2. Okay, so really you can replace the limit with lim sup, and then everything's even nicer, but that's only going to make sense if you've taken a real analysis course. So if L1 and L2 exist, then the radius of convergence R is given by 1 over L1 and also 1 over L2. And in particular, this shows that if both limits exist, then L1 and L2 must be equal. So it's kind of a corollary that we get here. I just want to mention that what we're doing is we're interpreting, I'm being slightly sloppy here, but we're interpreting 1 over 0 to be infinity and 1 over infinity to be 0. Okay, so that's how we interpret these. So if the limit if L1 is equal to 0, then R has a radius of convergence that's infinity, meaning that it converges on the entire complex plane. And likewise, if the limit is 0, then if the limit's infinity, then the radius of convergence is 0. So that's how we interpret that. We think of 1 over 0 as infinity and 1 over infinity as 0. So that's that. What I want to do though is I want to, again, not quite a proof, but let's think about this. So let's say, this is we can call it a sketch. It's not even really a sketch, but let's say that, I'm just going to call it L, so I don't have to keep writing L1, but let's say that L is going to be, and I'm just going to work with the root test, and I'm going to suppose that L is some positive finite number. Okay, so not infinity, not 0, because those are special cases in a certain sense. But let's let L be like 5 or 1/2 or whatever. So say L is this limit. Think about what that means. Think about what that means. That means that for all epsilon, there exists, for all epsilon, there exists a value n, capital N, so that the nth root of C sub n minus L is less than epsilon. Okay, and so just to be a little bit, I want to get rid of the precision, but I want to pick up an intuitive understanding. So let's say, let's say that if L is the limit as n goes to infinity of the nth root of the modulus of C sub n, then the modulus of C sub n is going to behave like L to the n. Okay, that's the idea, at least when n is large, right? So this really only happens when little n is greater than or equal to this capital N that we got from the limit. Okay, so this, I'm being a little bit imprecise here, but the modulus of C sub n is going to be close to L to the N. Okay, and so that's really the entire idea behind the root test. The reason why this is helpful is now think about this series. So if you take the series C sub n, z minus z naught to the n, and what I'm going to do is I'm going to apply the triangle inequality. This will be less than or equal to the modulus of C sub n times the modulus of z minus z naught to the n. And all we care about is when n is large, because that's when n is small, that doesn't affect convergence. That can affect what it converges to, but it won't affect whether or not it converges. So take whatever your favorite series is, throw out the first billion terms, and then study the rest of it. The rest of it is what determines whether it converges or not. So all we care about is when little n is large. So this is going to behave like the sum of, so again, you can, if you want, peel off, I'm being too precise still, but this is something like, if I wanted to be very careful, which I don't, you could peel off the terms up until n minus 1. And again, this is some finite number plus the terms starting with capital N. And again, this is the only value that's going to affect convergence or not. Okay, so now this is the thing that we have to look at, this last sum. And if little n is bigger than capital N, then this is, so what I said actually is not approximately, it's equal to. And now this is approximately, whatever this first thing is finite. Okay, so I don't really care what this is, but you get the first term. Plus this sum, which is going to behave like L to the N times z minus z to the N. And actually, I need to be really careful here. I need to be really careful here. Yeah, no, I don't. L is going to be a positive, well, a non-negative real number or infinity, because think about what the qualities are of the sequence here. C sub n is going to be a complex sequence, so you take the modulus that makes it a non-negative real number, and then you're taking the nth root. So, okay, so L, just by definition of what it is going to be a non-negative real number, so we don't need absolute values there. And so now think about this series. This looks a lot like a geometric series. And so this is going to be some stuff plus, basically it's going to look like we're going to have L times the modulus of z minus z naught to the n. And so it's really going to be a geometric series. And so this converges if L times z minus z naught is less than 1, okay, or if z minus z naught is less than 1 over L. So that 1 over L is why in the statement of the theorem, I'm going to scroll back up and show you, this 1 over L comes about here, right? So when we compute this limit, that 1 over the limit is the radius of convergence that we're going to get there. There are many technical details that I just completely glossed over. The book has a nice proof, an actual full proof of this result. The ratio test is very similar. It's actually left as an exercise in the book. And if this limit is equal to L, what this means is that, again, you get the same kind of long-term behavior. You have to argue a little bit differently, but again, you get that the sequence is approximately L to the N. Those are the values where you get this relationship. Okay, so if you have a sequence that's L to the N, that's when this can happen. And then the same argument works from there. Okay, so that's just kind of a real quick peek into the proof of the ratio and the root tests. Okay, so in the next video, we'll do some examples, and then in the final video, we'll talk about uniform convergence of series and how that all works.